All right, we're going to go through the practice final exam. This is for Chem 1151. So question one, which observation correctly reflects the colligative property? So we're looking for making it harder to boil or harder to freeze the more uh, particles we have. So NABR, so for number one, NABR, this is the same, they have the same molarity, so we're comparing them, is two particles. NABR minus. And then BaCl2 is three particles. Barium and two chlorines. So this one should have a higher boiling point because it has more particles, so it would make it harder to boil. And that's one is saying that this one has a lower boiling point. The sodium bromide has a lower boiling point. So that's true. So number one is true. All right, so for number two, NaOH has two particles, sodium and hydroxide, versus pure water. And pure water is one particle, but the word solution and molarity here means that we also have water in all of these solutions. So the water cancels out. So if you're comparing water to a solution of something in water, there's water in both. So we don't really look at the number of particles in water as a way to compare. So this one would have it would be harder to freeze, so it would have a lower freezing point because it's harder to freeze. So that's true. So automatically I know it's going to be E because I have, oh, sorry, it could be D or E. So I need to look at three actually. Pure water freezes at higher temperature than methanol solution. So a methanol, it's not an ionic compound because we don't know that name. It's actually a covalent compound. And the only reason I would say that you should know that it's a covalent compound is because it's not any name of any ionic compound we've talked about before. And it's actually CH3OH. This is not OH as an ion, but OH as, just like bonded together, an O bonded to an H. And so this has one particle because it is a non-electrolyte as a covalent compound. And so it would have a higher, it would have a lower freezing point. We're talking about freezing points in this one. So pure water freezes at higher temperatures, yes. So all three are correct. For question two, you have your reaction. What's the value of K? So K is equal to the products, which is B and C, over the reactants. The only thing we don't include in K is going to be like pure water as a liquid or any sort of solid. They don't tell us the states of matter here, so we just include all of it. And then we're just going to plug in. B and C are both 0.8, and A is 1.80. And so we get 0.356. And we can just choose D from there. But is it more reactant or product favored? Remember that if K is greater than 1, it's product favored, meaning the top of the fraction is bigger than the bottom of the fraction. If K is less than 1, it's reactant favored, meaning the bottom of the fraction is bigger than the top of the fraction. And if it's around 1, that means they're about the same. Question 3. So we're looking at specific heats. So if we have 10 grams of each of the substance and we put the same amount of energy in them, which one has the smallest change in temperature? So one way to think about this is mathematically. So if we have the Q is the same, the mass is the same. If I want the smallest change in temperature, what does the C have to be in order for this equation to work out? If the temperature goes down, the C has to go up. So it has to be high. Another way to think about it is that specific heat is the resistance, can't spell, to temperature change. So if it's more resistant to temperature change, it will change temperature the least amount. So higher C equals less temperature change. So we're looking for the lowest temperature change, so we're looking for the highest C, and that's going to be this one, liquid water. So we're talking about solubility for the next couple of questions. A hexane is completely nonpolar. If you only have C's and H's, remember that C's and H's are nonpolar. So we're looking for something with only C's and H's. All of these have O's in them except for D, which only has C's and H's. You want them to be similar. So like dissolves like. So we're looking for something that is similar, completely nonpolar. Now for the one for water, water is very polar. So we're looking for something with the most polarity, and it has hydrogen bonding. So we're looking for something that's similar to water, which automatically means this one is out because this is totally nonpolar. The rest of them are polar. This one has no hydrogen bonding because the hydrogen is not bonded to the oxygen. So that leaves us with these. I actually could argue E or A for this one. Probably A just because it's smaller, but E does have two places for hydrogen bonding. So you could argue E as well because two OH, two H bonding places. I don't think you'll see something that close, like between those two on the final. But between A and C, this one has more CH, more nonpolar parts than option A. So that's why option A is chosen here. But you could argue E. Because while it has more CH parts, it has two places for hydrogen bonding. All right, question 6. How many moles are of calcium chloride are in 250 milliliters of a 3 molar solution of calcium chloride? So remember that molarity is a conversion factor, mole per liter. Now you can do this algebraically, but I'm going to do this with dimensional analysis. So we can write this like this. And we know that 1,000 milliliters is equal to a liter. So we can start with conversion factor. I think it's always easier to do this because it requires a lot less processing and thinking than the algebra does. So we can clearly see that our math is set up correctly when we can cancel out our units. We don't have to second guess ourselves or get messed up with any sort of algebra. Conjugate base. And so if it's asking for conjugate base, we're assuming this is acting as an acid. So if water acts as an acid, it's going to donate H plus. If you get rid of an H, you get HO or OH. And then if you get rid of a +1, you get -1. So we put these two together to get OH minus. Question 8, asking for pH. The formula on your formula sheet for pH is negative log of hydronium. So pH is negative log of H. P just means negative log. So POH is negative log of OH. And then we're going to plug in the number into the calculator. And then we'll get our answer. For question 9, what's the hydronium? So if we look at the formula sheet, we have the opposite formula, 10 to the negative pH. And so we're just going to plug into that. And you should get something similar to this as your answer. Just plug into your calculator directly in that way. Molecular geometry of CH2O. So CH2O, Lewis structure looks like this. We have 1, 2, 3 groups around the center, which means we have a 120-degree angle. And if we draw in that 120-degree angle, it may be more helpful to get us to figure out the name of this. It looks like a triangle, so it's trigonal, but it's not a pyramid, it's planar because it's flat. In order to have the pyramid, we have to have the lone pair on the center, so planar for that one. So a pyramid would look like this. It's got three things bonded to it, but it also has a lone pair. So that would be the pyramid. So just be careful between those two. For which item does the ionic compound represent a correct formula? So we have aluminum phosphate. Let's just think about the formulas for aluminum phosphate. So Al3 plus, PO4 3 minus, there's one of each. So that's Al, PO4, one of each. So that's correct. Let's look at the rest of them. Aluminum oxide, Al3 plus, O2 minus. If you put that together, you get Al2O3, which is not what's written there. This one, magnesium and oxide, would give us MgO. So it's a 1-to-1 ratio. Magnesium and sulfate would also give us a 1-to-1 ratio. So 1 magnesium and 1 sulfate. So that means that the first one is the correct one. Which compound contains only covalent bonds? Well, this is ionic because it's ammonium and hydroxide, even though it has all nonmetals. You got to recognize your polyatomic ions. This is ionic because it has a metal. This is ionic because it has a metal. And this is an acid, so that means it is a covalently bonded thing, but breaks into ions in water. And it's not asking what it does in water, it's asking how is it bonded. So the answer is A. So remember, acids are covalently bonded. And when they're not in water, they're just normal covalent compounds. If we're looking for specific heat, this is going to lend me to look at this formula. We're going to solve for C. That's our specific heat. And then we can plug in. I like to always make sure I put my units in there when I'm doing algebra to make sure I have it correct. And now change in temperature is going to be final minus initial. Now, when it says releases, that means that the Q is actually negative. So that's why these negatives will cancel. Because negative Q, this is exothermic. So that means we're releasing that energy. Exothermic. So we should get 0.210. And if we look at our units, they should work out to the units of the answer. What is the percent weight volume? Oops. So weight volume is going to be grams and milliliters. And then we're going to times 100 to get a percent. So if we have grams over our milliliters, what of our total solution times 100, we should get 4%. Which compound can form hydrogen bonds with itself? So you have to have H bonded to N, H bonded to O, or H bonded to F for this to happen. And we have all these H's here and these O's and F's, but we don't have them actually bonded. So if you draw this out, CH4 doesn't have any O in it at all. This one doesn't have any O in it at all. This one doesn't have any H in it at all. Or sorry, this one doesn't have any O or F or N, and no O or F or N because it has H. So we're like kind of left with the other two here. So if we have this one, we're drawing it kind of like we see it, CH3, CH2, O, CH3. The reason they're kind of putting that O in the middle to tell us that this is the way that it looks. So kind of just draw that Lewis structure the way that it's written. You'll find this in Chem 1152 a lot. That's how we write to show Lewis structures a little bit more clearly. Instead of just combining all the C's, H's, and O's, it's actually showing you kind of how it's bonded. And then you have NH3, which is your obvious answer. If you have practiced Lewis structures enough, you probably have that one memorized. So you know that that has your NH bond that we're looking for. And the hydrogen bond, by the way, is going to be here. It's between the H of one and the N of the other. It's not the bond between N and H that I have highlighted in yellow. That's just showing me that I have the ability to do the hydrogen bonding. So because we have this, we can do the hydrogen bonding, but the actual hydrogen bond is between molecules because it's an intermolecular force, so between molecules. All right, so half-life problem. First thing we want to ask ourselves is how many half-lives has it been? So we start with 400 grams. We want to know how much left over after 70 days. So how many half-lives is this? If one half-life is 14 days, how many half-lives is 70 days? So we can just do a quick conversion using half-life as a conversion factor. And we have 70 divided by 14, so we have 5 half-lives. And then now we can cut our sample in half 5 times. So that's 1 half-life. That's 2 half-lives. That's 3 half-lives. That's 4 half-lives. That's 5 half-lives. That would be my answer. So first, you always want to ask yourself, how many half-lives is that? And that's either going to be cut it in half to figure out how many half-lives it is, or do this conversion to figure out how many half-lives it is, and then apply it to either type of problem. All right, so if we're neutralizing, we need to write a chemical reaction. We can't use M1V1 off the top of our heads because it's a dilution problem. Or M1V1 is for dilution problems, and this is a neutralization, so that means we have a chemical reaction. Now, we can use M1V1 if it's a 1-to-1 mole ratio. So that might be something that we want to check for first to see if we need to do a whole bunch of math. So sodium hydroxide is NaOH, hydrochloric acid is HCl, and we're going to write a chemical reaction. We're going to take our sodium, and we're going to put it with our chlorine. And remember, when we're doing these, we're thinking about those ions. Let me write the ions out. So sodium ions, hydroxide ions, hydrogen and chloride. We're going to put the sodium ion with the chloride ion on the right side. And because it's a 1-to-1 ratio, we get NaCl. And then we're going to put the hydroxide and the hydrogen ions together on the right side. And that's going to make H2O or HOH. And this is actually already balanced, so because it is a 1-to-1 mole ratio, we can use M1V1. So we can say V2 is what we're looking for. Our M1 is 0.5. Oh no, hold on. Let's think about, let's let me try to fit this in a little bit better here. Hold on. So we can use M1V1 here. So if our M1 is 0.50 molar NaOH, then we have our volume. Now these two have to go together. Do we see how these two have to go together? Because they're both about HCl, and there's language in between those two numbers that link them together. So if if this is my M1 about NaOH, then this must be my M2 about HCl. They have to be different. And then this must be my V2, the 150, because that's also about HCl, which means I'm looking for my V1 in this case. You could also, it doesn't matter if you pick who you pick for ones and twos, as long as they match up. So if we have M1 V1 equals M2 V2, we're solving for V1 here. And we just plug these numbers in, we should get 45. Why are buffers important in biological organisms? Buffers' job is to maintain pH, to resist changes in pH, not to maintain temperature, not to maintain amount of water. Yes, it might be a thing that, can happen from keeping from damaging, but to keep organisms from damaging, that's not what buffers do. The buffer's not guarding against organisms. It's guarding against different pH chemicals, right? Different chemicals that could turn pH into something dangerous. And then in electronic interfaces, no. So buffers, remember, they have a job to resist change in pH. What's being oxidized and reduced? So remember, oxidation is Leo and Gur is reduction. And Leo is a positive change and Gur is a negative change. So we have cadmium is going from 2 plus to 0. That's Gur, that's getting more negative, that's reduction. Zinc is going from 0 to 2 plus. That's Leo, that's getting more positive, that's oxidation. So who's being oxidized? The zinc. It has to be the thing that's on the left that's being oxidized because the zinc 2 plus has already been oxidized. So if it's asking you who's being oxidized, who's being reduced, it's always a reactant, not a product. All right, the following aqueous solutions does the weak acid exhibit the greatest extent of dissociation? So what does this mean? Dissociation means dissolving into ions. These are all weak acids. Which one dissolves into ions the best? So we're looking for the largest Ka means more ions because the ions of an acid reaction are the products. So if you think about a generic acid reaction with water, the ions are the products. So if you have a K or an acid, this is the generic Ka. We don't include water because it's a liquid. No H2O because it's a liquid. The rest are aqueous, meaning they're dissolved in water, so we can talk about them in terms of concentration. So we're looking for the one that makes the most ions will have the biggest top number, which means the Ka is going to be the largest. So we look over here, look at the exponents first. Don't look at the front numbers first. Look at the exponents. We have -2, -10, -7, -5, and -8. Think about what you'd rather have in your bank account. That's the biggest number. -2 is what I'd rather have, right? That's the biggest number. So -10 to the -2 is smaller, or sorry, is bigger, a bigger number than 10 to the -5, then 10 to the -8, then 10, whoops, I did that wrong. So 7, then 10 to the -8, then 10 to the -10. So that's kind of how we could rank them if we were asked to rank them. You only look at the beginning numbers of scientific notation if you're going to compare the numbers if the exponents are the same. Energy diagrams. What letter represents the enthalpy? So enthalpy is the difference in the products minus the reactants. So which line is products minus reactants? So if this is my reactants, these are my products. The difference in products minus reactants is B. What is A? A is the activation energy. Of the forward reaction. C would be the activation energy for the reverse reaction. because it would be how much I have to go, how much I need to put in to get up the hill if I went in reverse. And D is nothing. I mean, D is maybe like time of reaction. Nothing that we've really talked about. So B is your enthalpy, which is your products minus reactants in the forward direction. For 22, the equilibrium constant expression is this, true or false? All right, so we have all gases, we can include them. This would be on the top, so it would be NO to the 3 over NO2 over N2O, and that's not what we have, so we pick false. Remember, it's products over reactants raised to their coefficients. What would cause the change of a small amount of HCl to a buffer solution? So when we're talking about a buffer solution, and you want to know what is going to change to it, let's draw the buffer solution out. It's always the weak acid with water. So we'll put in our weak acid here and water. And we see that we're going to make the conjugate base and hydronium. If I add HCl and water go one way to make hydronium and chloride. 100% break into this. 0% of HCl is left. That's because it's a strong acid. So HCl is really like saying we're adding hydronium. If we add hydronium, we're going to shift to the left. If we shift to the left, this is going to decrease. This will increase. And so we pick option D. And yes, hydronium will increase, but because we're going to shift left, it's going to go back down again. So it's not going to increase significantly, right? It'll maybe only increase a little bit because the job of a buffer is to keep that hydronium around the same level that it was, which is why it has this equilibrium system. And when you have to have this there, because if you don't have any of that there, the conjugate base, if you don't have any conjugate base, you can't decrease it. And so you can't move to the left if you don't have something on the right to turn into the left. So we have to have this in order to react with any added acid to shift to the left. If we can't shift to the left, then it's not gonna do its job. What pressure will 3.2 moles of nitrogen exert if it's confined in here? So we have P, we have an N, we have a V, and we have a T. We have one of each. So we're going to use Pivnert for this question. You have to make sure that we're using all the units of R. So do we have all those units of R correctly? We have moles. That's correct. We have liters. We'll get ATM. We need to change this to Kelvin. So we're going to add 273. And then we can plug in. We're going to solve for pressure. So it'll be nRT over V. And then we'll plug in. I like to put in the units because it helps make sure that the algebra is correct. And then divide everybody by volume. This cancels out moles, Kelvin, and liters, leaving me with ATM, which is what I want. And I'll get 6.53. All right, we're going to continue the rest of this in another video.